Quantum mechanics was first introduced as a concept in 1901 by Max Planck, who wrote a paper about blackbody radiation. In this paper, he described an ultra-dynamic catastrophe, or how a piece of matter emits radiation depending on temperature. It was initially thought that the emission of light was proportional to temperature because, according to classical theory, energy is assumed to be continuous. In actuality, the intensity of energy emitted by temperature decreases with temperature, as discovered through experimentation. Planck's formula for energy is as follows: E equals N multiplied by H multiplied by nu. Here, E is energy. Energy moves in steps, so the integer n represents the steps energy can move through, such as n equals 1, 2, 3, and so on. H is Planck's constant and is equal to 6.626 times 10 to the negative 34 joules times seconds. Nu is the frequency and can have any value. The effect of radiation on matter that causes matter to emit electrons if it has a certain property is known as the photoelectric effect. This was a problem studied by Albert Einstein. Classical mechanics predicts that the emission of electrons would depend on the intensity of the light, not on the frequency of light. In reality, frequency affects the emissions of electrons, not the intensity of light. Einstein used Planck's quantization of energy to write the equation E equals h times nu. He called each jump in kinetic energy of electrons photons. Light is an electromagnetic wave with sine and cosine fluctuations, but it also behaves as a particle that interacts with matter. As a wave, light is delocalized, or in other words, not physical. As a particle, the mass of light cannot be measured. As light is viewed on a smaller scale, it becomes impossible to distinguish between a wave and a particle. The momentum of light can be quantified using the equation P equals h divided by lambda. Here, P is the momentum and lambda represents the wavelength of the light. Adjusting the first equation given for energy, the energy can also be written as E equals hc divided by lambda, where c is the speed of light as it is equal to 3.0 times 10 to the 8 meters per second. Another possible representation of the energy equation is that which is the most famous, E equals mc squared. Here, E still represents the energy and c still represents the speed of light, but mass is given by the variable m. When we combine these two energy equations and rearrange them a bit, we land up with an equation where lambda is equal to h divided by m times c. This tells us that wavelength is associated with mass. Every object with mass has an associated wavelength that becomes more apparent for smaller objects. In other words, everything that is a wave is also a particle, and everything that is a particle is also a wave. If you couldn't already tell, classical mechanics does not explain small matter very well, but it is still important because classical matter describes the motion of matter. When discussing quantum mechanics, it is helpful to go further and define Newtonian mechanics. Newtonian mechanics is how the objects move when subjected to forces or potentials. Newtonian mechanics uses the equations of motion that describe the position of a body, but goes further to predict the position based on an existing position and the object's momentum. There are two important equations of motion to know. Number 1, the differential equation representing the change in momentum over the change in time is equal to a function of f of the coordinate q. According to Hooke's law, that function f of q is equal to negative k multiplied by q, where k is Hooke's constant. Therefore, the change in momentum over the change in time is equal to negative k times q. dp over dt can also be denoted as p dot, and thus p dot is equal to negative kq. Number 2, the second equation of motion is also a differential equation representing the change in position q over the change in time, and is equal to the momentum p divided by mass m. Rearranging this equation can give us the useful expression for momentum, where p equals the change in position over time, also denoted as q dot, multiplied by mass. Thus, q dot is equal to the momentum divided by the mass. Once the position q and momentum p are known for some initial time t0, we can use the two equations of motion to calculate the momentum and position at any time in the past, present, or future. There are various ways to write the equations of motion. The first is the Newtonian version, which uses position and its time derivative. The Newtonian version relies on Hooke's law, which describes a body attached to a spring, but does not include energy. Here, the forces acting on the object change its position and velocity. Another method is the Lagrangian method, which uses the energies in the system, the kinetic energy and potential energy. This method uses a concept called action, which is to say the principle of least action calculates the same thing as the Newtonian. The Lagrangian method oftentimes makes the math simpler when solving problems. Finally, there is the Hamiltonian. The Hamiltonian is the sum of all energies contained in the system, that is, kinetic energy plus potential energy. All of the same information is contained in the Hamiltonian, but different math is used, making it even simpler than the Lagrangian for even more complex problems. In the Hamiltonian, the equations are still written based on position and momentum. Something important to keep in mind about the three ways to write the equations of motion is that the Newtonian, Lagrangian, and Hamiltonian methods all contain the same information, just written differently. They are all connected. Let's break down the Lagrangian and Hamiltonian even further. Starting with the Lagrangian. The Lagrangian rederives the equations of motion in terms of energy, and therefore describes the energy of the system. The Lagrangian is equal to the kinetic energy minus the potential energy. The kinetic energy is dependent on the position and momentum q and p, or q dot and q, while the potential energy is only dependent on position q. Note here that momentum and position are independent of each other, but are both required to understand the history and future of the system. Action is denoted by a capital letter S. S is equal to the integral from time t1 to time t2 of the Lagrangian multiplied by differential time dt. Using this equation, you can know every possible path taken by the particle between t1 and t2. The principle of least action then becomes very important. In the principle of least action, the shortest path is said to be the most convenient and should be used to determine the equation of motion. We should also assume the system is simple and that nature will always choose the shortest known path because it requires the least amount of energy. Thus, according to the principle of least action, the action S must be at a minimum, and ds divided by dq equal to 0 is true for maxima and minima. As a side note, the Euler-Lagrange equation only requires one equation, and an understanding of the principle of least action. This equation is given by the differential of the partial differential of L divided by the partial differential of q dot with respect to dt is equal to the partial differential of L divided by the partial differential of q. Hamiltonian mechanics, which is actually a concept of physics and not quantum mechanics, uses the two quantities position q and generalized momentum p. Here, momentum p is equal to the derivative of the Lagrangian divided by the derivative of position, also known as velocity, q dot. For more complex objects, the Hamiltonian can be written as the capital H equal to p multiplied by q dot minus L of q and q dot. This version is derived using the Legendre transform on the Lagrangian. The equations of motion are as follows. 1. P dot equals negative dh over dq. Number 2. Q dot equals positive dh over dp. Thus, the Hamiltonian is a function of p, q, and t, and is equal to the sum of potential and kinetic energy. The kinetic energy, capital K, is equal to p squared divided by 2 times m. The potential energy, capital V, is equal to 0 if the object is unable to move, but represented by capital V of q for the majority of objects. The potential energy may also depend on momentum. Using these definitions for kinetic and potential energies, the Hamiltonian can be reduced to a function of only p and q. In summation, the three mechanics are the Newtonian, which describes force and velocity, the Lagrangian, which describes position and velocity, and the Hamiltonian, which describes momentum and velocity. Moving into actual quantum mechanics now, quantum mechanics uses the Hamiltonian, which represents the total energy of the system. Schrodinger's equation is a very important equation as it is the analog to classical mechanics for particles that behave according to quantum mechanics. As we know, classical mechanics falls apart for small particles because they behave more like waves. The goal of the Schrodinger equation is to predict the system both at a future time and in the past to describe the system in space and time. Let's start with the equation of a wave. The equation of a wave is a function of x and t and is equal to Euler's equation of e to the power of I multiplied by the difference between k times x and omega times t. Expansion of Euler's equation shows that it has two parts, a real part and an imaginary part. The real part is given by the sign of kx minus omega t, while the imaginary part is given by I times cosine of k times x minus omega t. For real waves, the imaginary part will equal 0. 99% of chemistry is real and independent of time, so for chemistry purposes, Euler's equation is forced to be real. To determine how the wave moves in space, we need the energy of the wave. The energy of the wave will be dependent on speed, but observations only represent a frozen snapshot in time. Therefore, the derivative of speed is needed. Also, energy is dependent on more than just speed. A second derivative is required, or in other words, the angular coefficient of the first derivative. More simply put, we need constant acceleration. Thus, energy is directly proportional to the second derivative of position. There exists a time-independent Schrodinger equation, which predicts the past and present. I encourage you to look up the equation if you are interested. To solve the time-independent Schrodinger equation, two things must be done. First, you must solve the wave function, and second, you must find the energy. The time-independent Schrodinger equation is universal because it is valid for every system. There is nothing more fundamental than the time-independent Schrodinger equation. In contrast, the time-dependent Schrodinger equation accounts for time. It is used to make predictions about the past and future of a system. The time-independent Schrodinger equation is a special condition of the time-dependent Schrodinger equation. This has been an episode of Fall Asleep to Science. Thank you for listening.